Welcome to Mahatma Education Society's e-learning channel. This is the 23rd of a series of lectures on Introduction to Mechanical Vibrations. We are in the chapter Free Damped Single Degree of Freedom Vibration Systems. The outline of the lecture is the recapitulation of last lecture contents, superimposition of displacement versus time curves for different damping types. Then to find for underdamped 1 degree of freedom vibration systems the logarithmic decrement and how to find logarithmic decrement when we are given with the amplitude at the end of the nth cycle. Then we see the concept of equivalent dampers. In that we have viscous dampers in series and parallel arrangements and also inclined damper. And lastly we see the work done by a viscous damper. The recap. In the last lecture, we found out the values of the constants involved in the three different expressions for free underdamped single degree of freedom vibration systems, and using these values of unknown constants we put up in the final solution forms. The three forms of the solution for underdamped system are given as x of t is equal to e raised to minus zeta omega nt multiplied by a sine of omega dt plus b cos of omega dt. The second form is equal to a e raised to minus zeta omega nt multiplied by sine of omega dt plus phi, and the third form is equal to a e raised to minus zeta omega nt multiplied by cos of omega dt plus phi. Note that the values of constants a and b in the first equation and the value of the constants a and phi in the second and third equation forms are different. Nevertheless, for a given value of time t, we obtain the same value of x or the displacement for a particular time t. Then we looked at the variation of damped natural frequency with the damping ratio in case of underdamped system. So we have this formula: the damped natural frequency is equal to under root of 1 minus zeta square times omega n. So zeta is varying between 0 and 1 value. So we find that omega d is less than omega n always, right? So because of this we find that the Td, the damped time period, which is nothing but 2 pi by omega d, is found to be more than the undamped time period. Or I can say that in the presence of damping, the undamped system changes to a damped system and the time taken for completing one cycle is more. Or I can say that the system has become sluggish or lazy. Then we looked at the non-dimensional plot of the displacement versus time curve for the case of underdamped system, and then we concluded with the results. So the plot looked something like this: displacement versus time. So this is the curve denoting the envelope that is joining all the peaks of different cycles. So the displacement is actually occurring within this envelope, and the envelope is given by a e raised to minus zeta omega nt, which is a function of e raised to minus zeta omega nt, that is, it is exponentially reducing. The presence of minus in the exponential term indicates that the amplitude is reducing in value, right? So at least one cycle of oscillation is occurring in case of underdamped system. So there is the presence of a time period, a damped time period, at least one of these, right? And hence there is also presence of omega d. Okay, so the system is periodic in nature. The time taken for completing one cycle is the same for each and every cycle, right? Now we look at the superimposition of displacement versus time curves for different levels of viscous damping. So starting with undamped system, that is zeta equal to 0, then we draw the curve for underdamped system, then for the critically damped system, and finally for the overdamped system. So we now assume here that the system is given some initial conditions which are remaining constant for all the different conditions. So let me draw the plots. So this is the displacement, or I can assume the normalized displacement here, x of t divided by the displacement at time t equal to 0, right. So to start with, when time t equal to 0, the numerator also becomes x of 0 and we have the value starting from 1. Okay. So this is for convenience purposes. Okay. So let me draw these dotted lines denoting the constant amplitude, and this is a indicative of the time, right. So let us assume that I don't have any kind of initial velocity, there is only initial displacement. So talking about zeta equal to 0 or undamped system, we expect that the amplitude will remain same for different cycles. So the plot will be something like this: simple harmonic motion, okay, and this value is equal to a. So the equation for this will be given by x of t is equal to something like a cos of omega n t plus phi. Okay. So this is a cos curve, that's why I written over here. Similarly, you can also write a sin of omega n t plus phi, something like that. Okay. So in this case, phi is 0 over here. Now let me draw for the other conditions of damping. So this one is zeta equal to 0, right. I will proceed with the underdamping case, that is zeta less than 1. So what we can expect is the amplitude itself is reducing exponentially with time, and that forms the envelope. So let us assume that x of t for the case of underdamped system is a e raised to minus zeta omega n t multiplied by sin of omega dt plus phi, right. So let me have here the curve starting from 1. So I have the envelope that is a function of the exponential reduction, something like this, and also the time taken to complete one cycle will be more compared to the undamped case. So it should be something like this. So time taken to complete one cycle is the damped time period, that is 2 pi by omega d. The envelope is defined by a e raised to minus zeta omega n t. So we separate out the sine term or cosine term, and the value of this sine or cosine term can vary from 0 to 1, and because I am talking about the amplitudes, the value of this sine or cosine term becomes equal to 1. So we can associate this by 1, and whatever remains is the amplitude that we show it over here. That is a function of time and it changes exponentially, and minus indicates that the value is reducing. Now let me draw the plot for the case of critically damped system. So once disturbed, the system will try to come back without oscillation, but in minimum time. So this is zeta equal to 1. Now I will draw the curves for the overdamped system which are lying above the curve for the critical damped system. So once disturbed, the system comes to the rest position without oscillation. It's a case of aperiodic motion, but it takes longer and longer times as the value of zeta is increased. Okay, something like this, and ultimately I am having this zeta for infinite value. So this is zeta equal to infinite, and all these curves are for increasing values of zeta. Okay, so system becomes lazy or sluggish when the value of zeta is increased, and when I compare the critical damped system with the overdamped system, right, as zeta increases, the time taken by the system to come back to the rest position without oscillation also increases, and when I compare the underdamped system with the undamped system, the time taken for underdamped system increases as the value of zeta increases, right. Now we look at the logarithmic decrement. So it denotes the rate of change of the amplitude with respect to time, okay, or it's a case of the decay of oscillations happening over time. So by definition, it is the natural logarithm of the ratio of any two successive amplitudes on the same side of the mean line, right, and you're supposed to get this particular formula. Okay, so let us have one example of a displacement versus time plot, and let me draw some oscillations. So let us call this point as A and point B. So this denotes the amplitude at point A. Let us call it as x at A, and this is x at B, right, and the envelope that tries to connect these peaks is given by the formula A e raised to minus zeta omega nt. So let us follow this formula here. X of t is given as A e raised to minus zeta omega nt sine of omega dt plus phi, right. So separate the sine term, whatever remains is the equation for the envelope. So this is the time taken at point A, and this is the time taken for cycle to occur at point B, right, and the distance from here to here in terms of time is nothing but the damped time period, that is 2 pi by omega d, right. So writing for point A, I have x at point A is equal to, as per this formula, you can expect that this sine term is equal to 1, hence x at A is equal to A e raised to minus zeta omega n t at A. Likewise, x at B is equal to A e raised to minus zeta omega n t at B. The sine term becomes equal to 1 because it's a case of maximum displacement where the sine is equal to 1 value, right. Now let us take the ratio of these amplitudes so that I can relate both of these. X A upon x B is equal to, A cancels out, I am having e to the power minus zeta omega n T A minus T B. This can be written as e raised to minus zeta omega n. I can write here T B minus T A and some minus over here outside, and that becomes plus over here, right. That is also equal to e to the power zeta omega n. What is T B minus T A? That is nothing but the damped time period T D. That is also equal to e to the power zeta omega n. T D is 2 pi by omega d, and this is also equal to e to the power zeta omega n 2 pi, where omega d is given by under root of 1 minus zeta square times omega n. So note that we are talking about the logarithmic decrement for the case of underdamped system only, right. It is not valid for the critical damping or overdamping case. Hence omega n is cancelled out. We have this is equal to e to the power 2 pi zeta upon under root 1 minus zeta square. Now you can take log on both sides, and hence you will have ln x A upon x B, the natural log, that is log to the base e is equal to 2 pi zeta upon under root 1 minus zeta squared, and we call this as the logarithmic decrement denoted by delta. Okay. Now if I am given with the amplitude at the end of the nth cycle, then how to find the logarithmic decrement? Now let x0, x1, x2, x3 likewise up to xn be the amplitudes or the peak displacements at the end of 0th cycle, that is the initial peak, then the first cycle, second cycle, likewise up to the nth cycles respectively. That means I am having here displacement versus time plot, right, and I am having here some oscillations. Let me call this as the amplitude at the start of the first cycle, right, or at the end of the 0th cycle, both are same. Then amplitude at the end of the first cycle, at the end of the second cycle, likewise you are having amplitude at the end of the nth cycle. So you are given with the values of the amplitudes for the initial cycle and the end cycle, right, start of the first cycle and the end of the nth cycle, and in between there are n number of cycles covered, that also you will be given with the data, right. So how do I proceed with the finding of logarithmic decrement? Now I will take the ratio of the amplitudes at the start of the first cycle to the end of the nth cycle. This can be expressed as x0 upon x1 multiplied by x1 upon x2 multiplied by x2 upon x3 till xn minus 1 upon xn. What I am doing over here is multiplying dividing by x1, then multiplying divided by x2, likewise multiplying dividing by xn minus 1, right, so that they cancel out each other, and ultimately I am having the same ratio x0 upon xn. And how many times I am doing this? It is 1, 2, 3, 4, likewise up to n. So it is n number of times. Now I take the natural log on both sides. Ln x0 upon xn is written as ln of this entire thing. Okay, so it's a product. So I know that I can expand this natural log of a product by taking the natural log of each of these and then adding it separately, right. So it is ln of x0 upon x1 plus ln of x1 upon x2, likewise you go on adding, right, it is plus ln of n minus 1 upon xn, right. And I know that the value of each of these defines the logarithmic decrement, that is the natural log of the ratio of successive amplitudes, right. So it is delta over here, this also is delta, and everywhere I am having delta, this also is delta, and this is occurring n number of times, right. So I can say that this is n times of delta. Hence I can write, therefore delta can be written as 1 upon n ln of x0 upon xn, right, which is nothing but 2 pi zeta upon under root 1 minus zeta squared. So you have to remember this formula, it is important for solving the numericals. Now we see the concept of equivalent dampers. How can we combine different dampers into a equivalent single damper that gives the same outcome, right. This is very much similar to the springs in series and parallel arrangements. In springs we talked about the spring force, that is equal to the stiffness times the deformation. Here we talk about the damping force, that is equal to the damping coefficient multiplied by the velocity. So we make use of this while deriving the equations, right. Suppose I am talking about the series arrangement where the dampers are connected here end to end. Let us have some mass over here. So mass is having a displacement of x. So there is a relative motion between piston and cylinder for each damper. So this is C1 and C2, the damping coefficients, and relative motion is given by x1 and x2 between piston and cylinder. for each of these dampers, right? Now I know that the damping force is remaining same, right? It's a case of series connection, and the relative motion when added up will give me the displacement of the mass, right? So x is equal to x1 plus x2, and when I take the derivative of this, I get x dot is equal to x1 dot plus x2 dot, right? Why? Because I want the damping force which is proportional to velocity, right? Now I will convert this x dot, right, in terms of the damping force and the damping coefficient, and this will be written first for the equivalent damper. So this can be approximated by an equivalent damper, a single damper, right? I call it as C equivalent, and where this motion also is equal to x, right? So therefore I have here damping force divided by C equivalent is equal to, now I write it for this, it is damping force upon C1 for the case of first damper and plus damping force upon C2, and I know that the damping force is remaining the same for all the dampers. I cancel this out. Ultimately I am having from this the inverse of the damping coefficient for the equivalent damper is equal to the summation of the inverses of the each of the damping coefficients Ci, where I is equal to 1 to number of dampers n. Okay, so very much similar to the springs in series arrangement. So we replace the K's with the C's, right? Now we talk about the parallel configuration. I have here two dampers connected in parallel such that both are having the same relative moment of piston with respect to their cylinders. So I am having this x and this x, that is same as the displacement of the mass. And the damping force is distributed in some proportion between these dampers. So I am having here the damping force is equal to the damping force in the case of first one and plus the damping force in the case of the second damper, right? Now again I introduce the equation, damping force is equal to Cx dot. Therefore I write initially for the equivalent system, I have here C equivalent into x dot is equal to C1 x dot for the case of first damper. So it is say C1 and this is C2 plus C2 into x dot, and I know that both the dampers are having the same relative motion and hence the same velocity, right? So this can be cancelled out. Ultimately I am having the equivalent damping coefficient as the summation of individual damping coefficients, where I is equal to 1 to number of dampers, right? Now again I am talking about the equivalent dampers, and in this case we talk about the inclined damper. So again we have a spring that is inclined to the direction of movement of mass. Similarly we are having a damper that is inclined to the direction of movement of mass, right? Something of this kind. So this is displacement x, this is a damping coefficient C of a damper, and this damper axis is inclined to the direction of movement of mass by an angle equal to alpha, right? I want to convert this into a damper which is aligned with the direction of movement of mass, right? So the axis of the damper is in the direction of movement of mass, right? And this becomes C equivalent. So there is a equivalence between the two based on the work done by the damper. Okay. Now I follow the same concept here as I followed in the springs, right? So initially I have the displacement of the mass, right, and I take the component of this displacement along the direction of the movement of the damper, right, or in the direction of the damper axis, So this is the component I am taking. So the value of this one, what is that? Okay, so this happens to be alpha again, right? So this should become here x into cos of alpha. So that is nothing but the relative motion or relative displacement of piston with respect to cylinder of the damper, right? So once I know this, that is x into cos alpha, I want the damping force as provided by the damper, that should be opposite to this, right? And it's a function of velocity. So I have here c multiplied by x dot of cos alpha as the damping force that is aligned with the damper axis. I want to again take the component of this damping force that is aligned with the direction of moment of mass. So I take further a component of this force along the direction of the moment of the mass, and here again I am having alpha here. So take the component of this force along this direction, which is nothing but cx dot cos alpha multiplied by cos of alpha again, which is nothing but cos square of alpha over here, right? So if I draw the FBD for this mass for the equivalent system, here I am having mx double dot, and here I should be having c equivalent into x dot as the force. So let me write in terms of something into x dot over here, right? So this can be written as c into cos squared of alpha multiplied by x dot for the real system, which is having the inclined damper. So then you equate both of these, right? So separating out the x dot term, whatever remains over here is nothing but the c equivalent. So I will write here, therefore c equivalent is equal to c times cos squared of alpha. So very much similar to the springs which are inclined to the moment of the mass. Now we have the work done by a viscous damper to dissipate the energy in the form of heat between two instants, right? So piston is moving relatively with respect to the cylinder between two positions, and between these two positions, what is the energy that is dissipated to the surroundings in the form of heat? That is what we are writing here. Okay, so in short I will write it as work done by viscous damper is equal to, you have to take the integral between the limits x1 to x2, and we have the damping force that is given by cx dot multiplied by the incremental distance covered by the piston with respect to cylinder. So this basically is nothing but the damping force and multiplied by the distance. So force multiplied by distance is nothing but the work done, right? So the reason why I am putting minus over here, work done is always positive, right? So if I am integrating this thing and applying the limits first with respect to x2 and then with respect to x1, I know that the energy is less when the system is at position x2 than when the position is at x1, right? So energy at second instant minus energy at first instant will be a negative value, right? So as to make this work positive, I need to put a minus over here. Okay, so this becomes a standard notation. So instead of using the x as the coordinate, if I am using the theta as the coordinate, then I will be using this formula minus integral theta 1 to theta 2, that is the angular deformation limits, multiplied by, that is torsional damping coefficient into angular velocity multiplied by the angular displacement. Okay, now I will be writing this equations for a equivalent system, right? And then I will also be writing these equations for the real system consisting of n number of dampers, or it can be having a inclined damper also. So ultimately for the real system I will be converting the work done by the dampers is equal to minus integral of, let us say x is the coordinate. So I will be having some function of c, or the damping coefficient of a number of dampers over here within the brackets multiplied by x dot dx, Okay, so there might be a number of terms over here, and also there might be some parameters related to the radius of the disk or some other kind. Okay, so this is for the real system. So what I need to do is I need to compare this work done expression for the real system with that of the equivalent system, right? So instead of C, I will be writing here minus integral x1 to x2 C equivalent of x dot dx. So comparing all the terms over here, so the term within the brackets in the real system, this one can be equated to this, which is nothing but the C equivalent. Okay. So when you use the equivalent system method for solving numericals for mechanical systems, what you need to do is initially you want to write what is kinetic energy. You write something of this form, half into something of x dot squared, where this something is equal to m equivalent. Then you found out what is PE, potential energy, and it was written something like half into something of x squared, and this something was nothing but K equivalent. And finally you are writing the work done by the damper in dissipating the heat, right, between two instants. That is written something like this, minus integral x1 to x2 and the C equivalent into x dot dx. Okay. So you can put all these equivalent terms in the differential equation. So what does the differential equation look like when you use these equivalent terms? It is m equivalent x double dot plus C equivalent into x dot plus K equivalent into x equal to 0, or it can be I equivalent theta double dot if I am using theta coordinate, torsional damping coefficient Ct equivalent into theta dot plus torsional stiffness equivalent theta equal to 0, right? And by dividing throughout by m equivalent in the first case, or by dividing by I equivalent in the second case, what we have is, let us say I am having x double dot plus C equivalent upon m equivalent into x dot plus K equivalent upon m equivalent into x equal to 0. And here we have to remember that this thing within the brackets is nothing but omega n squared, and this thing within the brackets should be equal to, if you remember the contents covered in the last lecture, it is 2 zeta omega n, right? So this is very important here. Likewise you can write it for the second equation also, right? So 2 zeta omega n can be written as Ct equivalent upon I equivalent. Also omega n squared can be written as Kt equivalent upon I equivalent. Okay. So that's the end of this lecture. Hope you understood the contents. Thank you.